why do I care about this? Why do we want to study this? And I have three motivations in my mind. First of all, it's sort of a theoretical physicist's perspective is that we learn about forces and pressure from equilibrium. So when we think about pressure or forces, lots of what we say sort of stems from what we were taught as undergraduates or graduates. And the natural question is, if we go out of equilibrium or into active systems, we could ask what's different. Okay, is the same intuition, all the phenomena that we associate with pressure in an equilibrium system, does it just translate to a non-equilibrium system? Or can we find a host of new phenomena that we were not aware of in these new systems because there's something different? They don't obey the stuff that we've learned before. The other thing is more practical. Active systems use forces to do many things. So I'll call this applications. So for example, cells move. And you might wonder, what do they have to do to move? Do they have to do things that we've learned from equilibrium? And I'll get to it later. Or can they do smart things to move that was not in the toolbox of equilibrium systems? You could think about moving things in cells, some organelles. Or you could go to synthetic systems and think about, can we do smart things with forces in active systems like self-assembly? Can we do something smart with the forces so that maybe one day in the future we'll throw a bunch of active particles together and they'll build something non-trivial without us interfering or giving them specific orders? Another important aspect of pressure and forces in active systems is that if we're ever hoping of building something like thermodynamics for these guys, okay, not obvious at all, then pressure is an obvious state function. Okay, if we have a state function, that's a very powerful tool. For example, if you're studying phase separation and you have two phases in coexistence with one another, if you have pressure, which is a state function, if it follows the rule of equilibrium, then we look at the two phases and we know that both of them have to have the same pressure to be at coexistence. Similarly, if we throw any two in equilibrium, it's a very powerful thing. We throw two systems together, we know that at equilibrium, if we remove the right constraint, then we know that pressure has to be equal. So that's a very powerful tool about telling us the state of systems. Okay, so these are my motivations. You might have other. Come and tell me after the talk. By the way, please ask questions. And what I'm going to do is hopefully convince you that everything I've said here is can hold under. You'll see. Okay, hopefully it will be interesting, and I'll show you that the answers here are positive. Here, okay, future things, and here in some cases. Okay, so before embarking on the discussion of forces or pressure in active systems, I want to go back and think about pressure or forces in equilibrium systems or out of equilibrium systems. And I want to present three definitions of pressure, three expressions for pressure if you want. And depending on your background, where you grew up, what you studied, you might be comfortable with one expression or the other better. Okay? And what we're going to do is sort of list all these expressions. And I always like to think about physics as understanding the rules of the game and then trying to break them. Okay? And so what we're going to do is understand all these definitions of pressure and then identify where things might be interesting and different than what we know. And once we'll do that, we'll study a class of systems which fall in that box that we identify at the end. Okay? So what I want to do first is sort of a recap of what we all know about pressure. Okay, so there are several ways to define pressure. And what I want to do before I define them, I want to set the settings. So I want to keep the discussion very simple. So throughout the first part of the discussion, I'll consider actually a one-dimensional system. And through all the talks, I'll only do non-interacting particles, and I'll mention when we can generalize things to interacting. Okay, and there's been lots of work done on that. So I'm going to consider a one-dimensional system. And when we think about pressure, we think about some walls confining the system. So there's some walls that are specified by a potential. So this is x equals 0, this is x equals L, and there's a potential specifying the left wall, and there's a potential specifying the right wall, and there's some system inside. Okay, and we want to understand the different definitions of pressure exerted by this system. Okay, so the most basic one that you might have learned in high school is the energetic one. Okay, and I'm going to call that PE. And PE comes from thermodynamics. And we think of an isolated system that we do work on. So pressure in thermodynamics is equal to minus the derivative of the internal energy with respect to the volume, which is here the length. And what we're doing is we're making sure that the only change in energy is coming from work. That means that we're keeping the entropy fixed, no heat entering or leaving. And in addition, the number of particles is fixed. Okay, so that's the basic definition. And here we identify the pressure as a generalized force. The change in energy is equal to force times the displacement. Okay, so that's a very natural definition of a pressure for equilibrium systems. And of course, I could also use a different state function. I could look at the Helmholtz free energy and differentiate this with respect to the volume with the temperature and the number of particles in the system. We have a choice in thermodynamics to use whatever state function we want. Okay? Now, one of the things that we take for granted, which is, I think, a bit surprising, is that pressure really doesn't care about the shape of the potential. Okay, I might as well take the potential at the end of the system and make it really, really sticky. So I could put in something like this. So I'm clumping particles next to the wall, and it's still the same pressure. And the reason in thermodynamics is that the energy scales as the system size, L, and the contribution from the interactions of the particles with the wall, okay, so energy from wall, scales as L to the 0. And you can extend it to whatever dimension you want. So this guy is a completely negligible contribution to the energy of the system. Okay, and when I differentiate it, any contribution from the boundaries goes like 1 over system size. Okay, so this is pretty spectacular because That means that, you know, when you're an undergraduate, you do these calculations with a hard wall, but you could do it with whatever you want. And that is a manifestation of what I've said before, that pressure is a state function. Is a state function. Mathematically, I can express it in terms of bulk quantities. Okay, the most famous one is the ideal gas law. Yes? Yeah, thermodynamics is well defined in the macroscopic. Yeah, thermodynamic limits, etc., etc., etc. Okay, so it's a state function, and that's a very powerful thing. Okay, lots of thermodynamics is built around state functions, and pressure is one of those. Okay, so this is the most basic definition. If we think about active systems, they're eating energy all the time and dissipating it, so clearly this definition is useless. Okay, it's not going to help us. Okay, and I'll write that later. Okay, there's another definition that I'm going to call mechanical. So that's PM. And PM is what you, if I asked one of you guys at high school, okay, I don't know what you learned in high school, but if I ask someone in high school, one of my children, what's the pressure? Well, he'll tell me, well, the pressure is the force exerted by the particles on the wall. So I sum over the particles, and I calculate the force that they're exerting, each of them, on the wall. Okay, let me just denote it this way. Okay, so I'm summing over the forces exerted by each particle on the wall. That's why I don't have a minus. So I can just do a small massage and write this in this form. And then I identify this as the density of particles at point X. Okay? And I write the pressure. Let me put a hat here for a reason that will be clear in a second. And I write the pressure is the integral over the density times dxv. Okay, so that's an expression for the force exerted by the particles on the wall. Okay, and of course I'm interested in a statistical average. So what I'll do is I look at the steady state. Okay, and from now on I'm going to denote averages over steady state distribution in this way by angular brackets. And what I get is that it's the integral of dx, the density of particles, the mean density of particles, where this is the mean over a hat of x. Okay? So that's a mechanical definition of pressure. That's what a high school student would tell you, assuming that he knows what a derivative is. Okay? Good. So if we're happy with this, then if you look at this, so first of all, before jumping in, this obviously for active systems, I'm sort of jumping ahead, is a useful quantity. I can put a wall and just measure the forces exerted on the wall by the active particles. So this is something we might want to calculate for active systems. Now, in addition, if you think about equilibrium systems, I just told you that this guy really doesn't care. It's a really sticky wall or really repulsive wall. Whatever you put here, the pressure is the same. Okay? If I look at this expression, then the density definitely depends on the potential. The potential definitely depends on the potential. Okay? So somehow there's a magic, and this whole thing doesn't depend on the potential. Okay? And it's a one line, okay, 1.5 line proof. I'm going to do it. Okay? So I'm going to use the Helmholtz free energy. Okay, so the free energy is 1 minus 1 over beta times log the partition function. And the partition function, okay, I'm doing it really, really quick, is the sum. If I'm going too quick, slowly, if I'm going too slow, you know, make some faces, I'll rush myself. Okay, so I'm summing over all the microstates, and my weight is e to the minus beta, and I'm going to put here h, which is, so beta is the inverse temperature. I don't have to define this. kBT, if you insist on keeping the Boltzmann constant. H, oh, okay, let me write this expression and then explain. So this is the partition function. It's a sum over all microstates, integral over all the positions of all the particles and all the degrees of freedom, etc. H is everything in the Hamiltonian, including whatever you want, interactions, blah, 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 whatever you want. That's not the interaction of the particles with the potential. Okay, so everything that's not here, I clump here. It could be as complicated as you want. Okay, everybody's happy with this? Good. So now I have to use my expression for the pressure. Okay, so P E in this case. So I'm differentiating this guy with respect to L. So I'm pulling out a minus beta. I have another minus from there. So I have minus 1 over z from the log. And then I have sum over n, sum over I of the derivative with respect to xi of v of xi minus L times e to the minus beta h plus sum over I v of xi minus L. Okay? All I've done is I've used this definition. Nothing more. Okay? Now I'm going to do something that you don't like. Okay, I'm going to change this derivative to a derivative with respect to L and get rid of this minus sign. Yeah, question? H will not depend on L. The only confining potential is the potential. Okay? Yeah, so this is that's what's defining the box, this potential. The energy will, but that will come out automatically from here, right? Okay, that will come out from the fact, yeah. Yeah, will be proportional to the system size times the density, right? So. Well, wait, what are we talking about? The energy? Yes, so the energy of the sum of, just think of an ideal gas. The energy of an ideal gas, well, just think about, for this case, sum over pi squared over 2m. Sum over all the particles. Yeah. Yeah. There's no, in the interaction Hamiltonian between the particles, there's no explicit L. That's all I'm saying. Okay? Okay, good. Now if I identify this guy, I can read off the density, right? The density is just the probability of observing a given configuration. I'm skipping one quick step, really quick step, but you can see that this will essentially give me is this too quick? Okay, I think it should be clear that this is equal to the integral of dx of rho of x dxv. Okay, if it's not, okay, if it's not, let me know. No? What? Okay, so the probability of observing a given configuration of the system, right? So the rho of observing a given configuration of the system, all the configurations x1 to xn, if we have n particles in the system, is just e to the minus beta h, which is a function of all these guys, which I haven't written down, plus sum over v of xi minus L divided by z. Okay? And if you use that, then you obtain this. Okay, that's all I'm saying. Good. Okay, so what I want to stress for this guy is that note that the Boltzmann distribution was crucial for this result. Specifically, the fact that I have this this equivalence. Okay, I was using explicitly the form of the Boltzmann distribution. Okay, and you might wonder, if we're out of equilibrium, what happens? Do things become very different or not? Yes. All the xi's, yes. Sorry? No, okay, so sorry, I messed up. You see, I should stick more with my notes. Sorry. Okay, so, yeah. Okay, sorry, I was, my bad. Okay, so F is equal to P, E is equal to minus dF dL. I sort of rushed in my own brain. So initially, when I differentiate with respect to L, I have this guy with a minus here. Sorry, in the notes it's fine. This guy with a minus here. Okay? Then I actually change the minus here and get the dxi here. Okay? And then I'm good to go. Okay? Sorry. Thank you very much. Okay. Yeah. Microstates. So it will be integral over the positions, momenta, all other degrees of freedom. Okay, good. Okay, but again, the fact that PE is equal to PM really rested on the fact that I was using the Boltzmann distribution. Wouldn't have worked otherwise. Okay. So the last definition is one that you might be less familiar with, again, depending on your background. But the next definition is through momentum flux. Okay, so the origin of this definition, which I think you've used over the last few days and the talks on fluid mechanics, the origin of this definition comes from continuum mechanics. Okay, and the idea is the following. We consider a momentum conserving system. Okay? So in the bulk of the system is conserving momentum. Okay, and I'm assuming that the dynamics are local. Okay, so I can write down an equation for the density of momentum in the system. Okay, so remember we're in one dimension. And if you want to think what's the definition of the density of momentum, then it's sum over I mvi times delta of x minus xi. Okay, it's the density of momentum at point x in the system. Okay, and if momentum is conserved and my dynamics are local, then that must satisfy this continuity equation. Okay? So Jp is the flux of momentum. For non-interacting particles, it's a very intuitive quantity. So for non-interacting, this guy is just sum over I mvi vi delta of x minus xi. Because it's the flux, so it's moving with velocity vi of momentum mvi. Okay, so that's the flux of momentum through the system. So then the definition of pressure is the following. We look. Okay, I should have kept this, but never mind. So we consider a fluid in rest, okay, and then define the momentum flux definition of pressure as the steady state average of the momentum flux at some point in the bulk of the system. So remember, angular brackets are denoted by angular, denote the average over the steady state. X is some point in bulk of system. Okay? And that's also defined as minus sigma. It really should be xx, which is the xx component of the stress tensor. Okay? So that's a definition through continuum mechanics of pressure. And it's sort of intuitive because momentum is flowing, and if I'm a hard wall, that's what it's hitting me, and it gives me the pressure. Okay, so note, by definition, this is a bulk quantity. Okay, so it doesn't care about the walls. So you're worried about the walls affecting the steady state distribution. Okay, so let's assume for the sake of this talk that that doesn't happen. That's a very good question, though. Okay? And we'll actually tackle that towards, if I get there, I'll tackle that towards the end. Okay, so this is a bulk quantity, and you might wonder, how is this equivalent to the other definitions of pressure? For example, this definition of pressure. Okay, because this looks like it's completely detached from all these definitions. Okay, so so comment. It's easy to see that PM is equal to PP. So the mechanical pressure, if I have a system whose bulk is momentum conserving, it's easy to see that PM is equal to PP. So to see that, what we have to do is introduce the wall into the system. Okay, so I'm writing the wall in the system. So the changes in momentum is equal to minus dx of the flux of momentum. But then the wall is exerting a force on the system, and that's acting as a momentum sink, right? There's a force acting on the particles, and that force is changing the momentum. So that's how a wall enters the equations of motion for the momentum. Okay, it's the force. Okay, so now let's look at the steady state. So at the steady state, we have that the average of rho dxv is equal to minus the average of dj p hat. Okay? So the way to think about this is a local force balance equation. Right? The change in momentum is caused by a force. So this is a force. And these two forces are balanced. Yeah. Yeah, I wanted to keep the fluctuations actually. Yeah. No, we haven't. That's just the definition of the instantaneous flux. How it evolves is a different. We can discuss that. Okay. Good. So now we're almost there. Remember, this is our definition of the mechanical pressure. So to obtain the mechanical pressure, all we have to do is integrate this guy from the bulk until to infinity. Okay, I have a feeling that I'm sort of, okay, I should go slightly slower. Okay, so the pressure, the mechanical pressure, is equal to the integral from some point deep inside the system to infinity of rho dxv. Okay, so this is rho, I remind you, is just the average of rho hat. Okay, and that from this equation is equal to the integral minus, I'm putting the minus ahead of time, of x star to infinity of dx of jp, the average of this guy, dx. Okay, now this is a full derivative, and lo and behold, we got our previous result. Okay, so just to recap, sorry, I feel like the last was last clear. We had a simple thermodynamic definition which relates to the change in energy of the system. The second definition was a mechanical definition. It's just the force exerted by particles on the wall. And what I showed so far, that at equilibrium, as they have to be, the two are exactly the same. Okay, that has to be. If it wasn't true, then many of the things that you like would break down. Okay, and the last thing I've shown you is if I take a system which conserves momentum in the bulk of the system, whose dynamics are local, then I can show that in these systems, the mechanical definition of the pressure is identical to the momentum flux definition of pressure. Okay, and this results, without noticing, you've been using all your life in one sort of another. All these results you've been mixing, you use one definition, another, you don't really care, you don't really check. They're all equivalent for the systems that we care about. Yeah. No, no. The fluid, because I'm assuming that it's not, I'm defining the stress tensor as the pressure as the component that's not due to flow. The average, no. Well, the average momentum is zero, yes. Thank you. Yes. Not the average momentum flux, the average momentum, yes. I want to get rid of the flow. Okay, so the comment I want to say here is exactly what Olivier said. Note that for any momentum conserving system, the pressure PM equals to PP, and is plus is an equation of state. Okay, so if you have a momentum conserving system and you have the setting that I've described here, there is an equation of state. You're guaranteed by the structure of the equations. No, not related to incompressible. No, it could be compressible. The only thing I've used is conservation of momentum, and the fact, and we'll get to it in a bit, and the fact that the wall acts in this way. Okay? Somewhere in the bulk of the system, yes. Deep in the bulk of the system if you want to be really careful. Okay? I don't know. What do you want? Well, I can express it in terms of bulk quantities. I don't have to specify anything. Yeah. It was constructed in the bulk, and all I have to do is I have to do a measurement in the bulk of the system, and that's it. I know it. I don't have to deal with anything. I don't have to know anything else, just what's happening in the bulk of the system. That's what I want. Okay, I'll try to. I have a feeling that I've confused you, but let me try to make some comments, and then hopefully some of the confusion will go away. So the first one is actually, the first comment will confuse you a bit. It's a small homework. It doesn't take a lot of time, so don't shy away from it. So comments. Okay, so the first one is trivial. In equilibrium, PM is equal to PP is equal to PE. Okay, so that's what I was trying to argue, and that's the equation for it. As a small side note, equilibrium is equal to, by what I've constructed, conservation of energy. Okay, we thought about an isolated system, no heat going in, going out. Doesn't have to be the case. We can think about an equilibrium system in the presence of a gravitational field. Okay? So can think about equilibrium system in gravitational field. Okay, that's probably a calculation that you've done sometime in your past. Okay? But what I'm going to do is I'm going to give you a homework, straightforward one. Consider an ideal gas and think about PM and PP and see if they agree. Okay, that's small. So an equilibrium system in a gravitational field. So no conservation of energy. Okay, no momentum. Okay, and what I'm telling you is calculate PM and PP. PP you do by what you've done when you were doing this in class. You look at a small layer of fluid and you do the balance of forces. So you think about this equation. Okay, so do that and compare the two. In some sense, this is a precursor to some of the things that I'll be discussing. This trivial example. Okay. So again, equilibrium, all these guys are the same. We don't have to worry. Use whatever you want. Life is easy peasy. That's an exaggeration, but I'll leave that. Okay, so other comments. So depending on system, and I'm specifically now discussing systems which have an equation of state, but from what you know, one definition, okay, depending on the system, different definitions might lead to equation of state. Okay, and I know that's slightly vague, but I'll try to fix this in a second. So for example, one of our things that we learn again as undergraduates is osmotic pressure. Okay, so that's an equilibrium system. So we know that we have an equation of state. Okay, if I'm thinking about an equilibrium system and I'm measuring the osmotic pressure of an equilibrium of this system. So no, in equilibrium, have equation of state. Okay, so that's a given. But the mechanism responsible here for having an equation of state is the first one. Because osmotic pressure, we have a wall that and the wall can let fluid inside and outside. So that allows for another term to enter these equations, because I might have a flow of momentum inside or outside from the system. So the reason that I have an equation of state in this system is because it's in equilibrium. It's not related to momentum conservation. It's not that they all apply equally. Okay? And I'll get to that, back to this in a second. I could also think about a non-equilibrium system. So non-equilibrium system plus momentum conservation So if I have that, no need to worry. Everything's as we expect. We have an equation of state. Okay, guaranteed. I don't have to think at all. Okay? Okay, something that I said before, but I want to reiterate so you have it in your notes. For active systems, PE is useless. Okay, there's nothing to elaborate about. Okay. Now, many active systems are such that they don't conserve momentum. Okay? So one example we could think about an active system exerting an osmotic pressure, and then the argument that I said before breaks down. Or I can think about experiments that, for example, Olivier is doing, but many other people are doing also with colloids, where the particles are actually moving close to a surface. If you're moving close to a surface, the system is not conserving momentum. You can always transfer or receive momentum from the surface. Okay? So the question is, we have an active system that's out of equilibrium. Okay? It doesn't conserve momentum. And the natural question is, what about the mechanical pressure? What properties does it have? Specifically, you might wonder, because all of the logic that I've given you before told you that energetics leads to an equation of state, the conservation of momentum leads to an equation of state. For the active systems, both of these break down. And now if I remind you the definition of the pressure, it's this guy. This guy depends on the potential in a non-trivial way. This guy is the potential. So what about active systems? Do they obey an equation of state or not? Is there an equation of state? And if there's no equation of states, what are the consequences of this? Okay, so that's where these lectures are going. In my clumsy way, I think I got there. Okay, so the question that we're raising is there a lack of equation of state? Okay, so we sort of isolated what might be an interesting case to look at. And if there is no equation of state, what are the consequences? Okay, so just one, before jumping into this question, just one comment about words that people use in the literature. People tend to classify active systems into two classes. The first are wet, and by that I mean conserve momentum. Okay? And the class that I've sort of tried to argue where interesting things might happen are dry systems, when there's no conservation of momentum. Okay, so these are just words. When you open an abstract, it typically tells you if it's studying a wet or a dry system. Yeah. 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 It is, because this is a bulk quantity. So the only, you might worry that the steady state in the bulk is influenced by the shape of the boundary. Okay? That's something that you might worry about, and it's a good thing to worry about. Okay, I might get to hints of that in other systems later. But as long as the bulk is independent of the shape of the boundaries, then it's a guaranteed result. Okay? Okay. So this we can... I think, okay, it's a very good point, and there's actually a recent, there's some recent, I'm not an expert on wet systems, and I'll describe similar results. Hopefully, the way I'm proceeding, it's not clear. But there are results that people now argue that boundary conditions are very important even in wet systems. In wet also. Yeah, we can, what? Yeah, yeah. PP, okay, that's again a wonderful question. I can define PM. PM, no problem, do the calculations. So if I have enough time, and then I'll define, I'll make sense of all of this at the end and show you once I get to it. Okay, so I'll run a bit forward and I'll come back to it later. I'll show you that generically there's no equation of state. Okay, and I'll discuss the consequences. Nonetheless, there are special cases where there is an equation of state. When you have an equation of state, that's a wonderful thing because you can use it for all the things that I've described before. So we better understand that. And at the end of these lectures, if I do my job properly, you should understand why there is an equation of state when there is an equation of state. And when I do that, I'll define a modified version of PP which you can use. Okay, and it will be in some restricted fashion. Okay, so that would be aim of the first part of my lectures. Yes?
Why do boundaries matter for light systems?
Okay, I'll show you when we get to these systems, I'll show you it. I don't want to steal my talk. Okay, okay, but let me rush a bit forward. If you have asymmetric boundaries, then the system out of equilibrium when you have an asymmetric potential likes to generate currents. We call those ratchet currents. Okay, and ratchet currents can lead to long-range effects. Okay, and so that's an interesting thing to think about. Yeah. Yeah. Okay, that I go into the bulk, I measure things in the bulk, and I know the pressure. I don't have to know the boundaries. You see, it could be, look at this expression again. It could be that to know the pressure, you have to tell me the shape of the wall. That's a horrible thing. Okay, but I'll show you that it happens actually. So, yeah. Have? Yeah. Yeah. Why not? Okay, this is outside my expertise. If there's I don't, you see there's a pressure term in fluid mechanics equations. Because it's moving, but suppose that, again, remember my definition, a stationary fluid. Okay? Yeah. Okay? Yeah. No. If you're moving next to a surface, you're transferring momentum to the surface. If you're in osmotic pressure, you can have fluid injecting momentum into the system, not through the rho dxv. I could be injecting momentum into the system, which is not related to the term that I wrote. Somewhere, if I include everything, then of course you're right. Okay? Yeah. Yeah. Mechanical equilibrium. Well, if I have an equation of state and I connect to, I think what you're alluding to, I connect two systems, and then they have to have the pressure the same in both of them, yes. Yes. Okay. Okay. So just to summarize again, we've identified the class of systems where something exciting might happen, and that's what I'm going to pursue. Okay, so the plan of my talk, after an hour of speaking, the plan of my talk is as follows. So we identified, just to identify, we need 1, non-equilibrium, and 2, no momentum conservation. Okay, so that's where interesting stuff might happen. And the plan of my talks is as follows. And we'll see how much I cover. So there's plan A1, which is what happens if you keep on asking questions and I answer patiently and everybody follows what I'm talking about. And what I'm going to do is I'm going to define a simple class of active systems. Okay, and it's really, really simple. Ideal gas, not even Ising model. Okay? Ideal gas, no interactions, and I'll tell you, we have results for interacting. I'm just going to mention them. And on the line, I'm going to make a small detour, and that will be important for plan A2, and discuss steady state distributions. In these systems. Okay? And what I'm going to focus on in this part of the talk is I'm going to look at PM and ask if has an equation of state. Okay? And the answer will be, so in red is what I want you to remember. The answer is typically no. And I'm going to discuss the consequences of that. And then, just to annoy everyone, in some cases, yes, and it's great if we have one, so we want to understand why we have an equation of state. And when we have one, I'm going to define PP and relate to PM. Okay? It's in brackets because it's you'll see it's a subtle thing, but it's there. Okay, so this is plan A1. And plan A2, I'm going to shift gears. Okay, so plan A2. And what I'm going to do is I'm going to look at isolated objects. So far, the focus has been on the setup that I've described before. We're going to do a lot in 2-dimension. But what I want to do now is think about some object of arbitrary shape sitting inside an active fluid. Okay. And what I'll show you is, and this goes back to some of the things I said before, that these generically experience forces which are related to currents which they generate. Okay? So in red is what I want you to remember, even if you forget my face, is if you have non-equilibrium, a non-equilibrium system, then generically it's easy to generate currents. Because currents are easy, steady state distribution functions are non-local. Okay, that's one thing I want to hammer through. Things are non-local. If you put a potential here, it's generically affecting the probability distribution throughout the system. Okay, so it's not as fun as equilibrium. It's more fun than equilibrium because of that, sorry. Okay, and these are all related to forces exerted in the system. Okay, so that's the master plan of what I hope to achieve. Any questions before I dive into looking at specific systems? Okay, good. Okay, so I'm going to dive into the simplest, I think, not offending anybody, I hope, the simplest dry active system known to man. Okay, so simple dry active system. And again, my plan is take this interesting system, take one class of models, and really study how things behave in that class of models. Okay, so the class of models that I focus on are called active Brownian particles. Okay. If you like shortcuts, ABPs. Okay. And I'm going to look mostly at non-interacting particles. Meaning that I'll also only mention when we have results for interacting cases, but I won't write any equations or nothing. We have them. You can come ask me, look, or Julian, or look them up. Okay. Now, before I jump, really I'm interested in pressure. I had the expression here for PM. This is the worst teaching you could do, the equation that was here. And to do that, I have to tell you what the particles are doing inside the wall. But before I tell you about what's happening inside the wall, I'm going to tell you about what's happening far away from the wall in 2 lines. Okay, so the model, equations of motion, no wall at the moment, and they're very simple. So what I want you to have in mind are ellipses. You could think of circles, but they're in 2D at the moment. 2D, sorry. And these ellipses have an arrow assigned to them. And the arrow is telling the particle in which direction it's moving. So there's some force that's driving this particle in the direction of the arrow. Okay, so the particle is being pushed in the direction of the arrow, but there's some noise that's changing the direction of this arrow, some rotational diffusion. Okay, so if I track this particle, it's sort of moving about and doing this motion. Okay, so let me write down the equations of motion for this guy. So if I have I equals 1 to n particles, the I is really redundant in what I write here. Then Ri dot, so this is the position of my ellipse, okay, the center of the ellipse if you want. And then it's moving with velocity v, so that's the activity, that's the force that's driving the system out of equilibrium. Okay, and it's pushing the particle in a direction which is related to the direction of the arrow degree of freedom. So theta I is the direction in which the arrow is pointing. So this is cosine theta I, sine theta I. Okay, and this is, if you want, theta. Okay, and on top of that, I'm going to throw in, this is actually an experiment. This is typically completely negligible, but I'm going to throw in thermal noise. Okay, Olivier, in your experiment, you probably never saw something move from thermal. Okay. Okay, but it's not thermal. Okay, good. So we have some noise. So this is a random force term. I'm assuming that everybody knows what the Langevin equation is and how to go from a Langevin equation to a Fokker-Planck equation. If you don't know how to do that, come to me. I'm just running a bit slow. Come to me after the talk. Either I teach you or I give you notes where it's done. Okay? It's not very hard. Okay? So this noise, so this noise obeys that the average of eta I of t is 0, and the correlations eta I of t in direction alpha, eta j of t in direction beta is delta alpha beta, delta ij, delta of t minus t prime. So it's white noise drawn from a Gaussian distribution, and it's uncorrelated between particles and in different directions. Okay, so this is the dynamics of the center of mass. Of course, I have to tell you what's happening with the angle degree of freedom. And the angle degree of freedom obeys the simplest thing that you might obey, which is 2 dr times psi of t, which is again white Gaussian noise. Okay? So again, I'm not going to, I'll write it. Psi I of t is equal to 0. It should be an I here, and the correlator okay, good. Okay, so you can actually do several things with this model, but I'm not going to analyze it a lot. The simple question is, if I look at these particles on large length scales, whatever I do, they're just diffusing about, right? It's a particle that's changing direction randomly. All it can do is just diffuse about. I have to be honest, when Julian first told me that he was working on these things, I thought, really? And now here we are. Okay. Okay, so they're just diffusing about, and you can actually derive the diffusion coefficient of these guys. So particles diffusing, and you could argue for the diffusion coefficient in many ways. And there's an effective diffusion coefficient. I'm neglecting the contribution from this guy, which is just given by v squared over 2 dr. Okay, you could argue for this from dimensional analysis. We have v and we have dr, so that's what has dimensions of a diffusion constant. Or if you want to be slightly more more precise, you could go to kinetic theory and argue that the diffusion constant is 1 over the dimension times the velocity times the persistent length or run length, the length before the particle changes direction, which is v over dr. So every v over dr, to a good approximation, the direction of the particle is chosen at random again. Okay, so these guys are just diffusing about, nothing exciting at the moment. If you want to think, why do these guys break time reversal symmetry? Well, there's lots of work right now discussing this in great detail, but I'll give a very simple argument. If you run the movie backward in time, the arrow is still pointing in the same direction, so there's no time reversal symmetry. Okay, so when v is different than 0, we're out of equilibrium. V equal to 0, equilibrium. So we have a handle for when the system is in equilibrium and out of equilibrium. So this is, as again I told you, probably the simplest model that you could think about. There's a variant of this guy that people study a lot, which is called run and tumble particles, where instead of doing rotational diffusion, the particle stops and with rate alpha changes direction randomly. All the results that I'm going to show you just translate with trivial modifications to that case also. Yes? Yeah, yeah, yeah. Yeah, that would work, but let me stick with this, okay? That would work, and people have written, if you calculate the entropy production with this or without that, you get completely different results. I'm happy with this version, but I'm happy to also discuss it later. Okay, good. So I defined the model, not, you're probably, yeah. Well, but then I have the contribution from this guy, which I've neglected. So yeah, yeah, yeah. Okay? Yeah, you just sum them. Okay. Okay, good. So so this is pretty boring, but now we want to remember we're forces, pressure, and active systems. So now I want to calculate PM for the model. Okay, so to calculate PM, I have to tell you what's happening when the particle gets to the wall. Okay, so I have to specify. Yeah. Yeah. Sorry, I was planning to say that, but it's okay. It's getting late in the hour and a half. In Israel, we teach 50 minutes, so this is okay. So if you look at the dimensions, this has dimensions of 1 over time and not of a diffusion coefficient like you're used to. Okay, just looking at this equation. Okay, so now I have to specify what happens next to the wall. Okay, so so I'm going to put a wall here. Okay, and it's not a hard wall, it's described by this potential V of x. Okay, because I'll be interested later in what happens when I change V of x. Okay, so I'm going to write down the equations of motion. I'm going to rewrite them again with the trivial modifications due to the wall. So the first thing is, if I add a force due to the wall, then these guys are unchanged. But now I have a force that's exerted by the wall. So when the particle enters the wall, it's experiencing a different force, which is changing its velocity. Okay, so that's as simple as it goes. Okay, and the other thing is the dynamics for the angle theta. Now I've started with ellipses on purpose. When an ellipse goes into a wall, it feels a torque. Okay, it feels a torque that wants to rotate it because there's, okay, just because it is. Okay. So if I have an ellipse, it's not feeling a torque when it's like this. When it's like this, it's feeling a torque that's rotating it here, and again, it's not feeling a torque when it's in this direction. Okay, I'm going to keep this general and just say that in general, when it enters the wall, there's a torque that depends on position and the angle of the particles. So this is the analog of the velocity. This is a guy that's actively rotating my ellipse. Okay, if it's a circle, no torque. If it's an ellipse, there is a torque. And we'll come back to that later. And then I have my rotational diffusion. So that was dr, right? What? The arrow, that's what's happening. The torque is rotating the ellipse. Well, if you just think of you could think of models like that, but the simplest model, you would need an ellipse to feel a torque. Okay? Yeah, if you have friction, you could do that, but I'm just thinking of. Okay, and the torque for the simplest for a wall of this shape, the simplest form of the torque, it would be something proportional to sine 2 theta. When theta is 0, there's no torque for an ellipse at least. Yeah. 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 Nothing. Well, you could. All the results will be okay when I turn v equal to 0. I'll go back to equilibrium. Okay. So now I wanted to calculate PM. You want me to calculate it? I have 10 minutes and I want to. Okay. 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 I'll tell you. I'll sketch the derivation. No, that's a bad idea. Okay. So I'll do it. I'll try to sketch it tomorrow. I'll just jump to the result. Okay. Okay, so I'm going to, so we calculate PM, and V is here, and V is somehow hiding here. Okay, and you can do that. You write down a Fokker-Planck equation, and it's really a 4-line calculation. 4.5 lines. Okay, nothing fancy. Okay, and the expression we get is this one. So this is the density in the bulk. Okay, and then we have dt over mu, also known, so this is the translational diffusion coefficient divided by mu, also known as kBt. Okay, not very exciting so far. Okay, but again, remember we have this effective diffusion coefficient. Okay, so you might guess that we also have this contribution. Okay? So this is what you would guess. If I told you guess the equation of state for the pressure, I would tell you if they're diffusing, that's what you have. Okay, and I'll comment about that later. It turns out, however, that there's an extra term which is proportional to V. Remember, that's how, if V is non-zero, we're out of equilibrium. Okay? It's mu over dr, and then we have the integral of dx gamma, and it's a wall. It's a wall that's parallel to the y-axis. I'll discuss hopefully later other more complicated walls. Sine theta px of theta d theta. Okay, so finish copying and then I'll say a few words. Okay, so again, this is what you would guess. Nothing exciting going on here. But now we have this term. It occurs only when the particles are experiencing a torque. Okay? This torque depends on the potential, right? Because the torque comes from the potential. This probability distribution is the probability of finding the particle at position x at angle theta. That depends on the potential. Okay? It turns out that there's no miracle here. This whole term genuinely depends on the potential. So it means that if you measure the mechanical pressure with a hard wall or with a sticky wall, you get different results. Putting it in different terms, if you buy your pressure stat from different companies, you might get different results. Okay, the pressure is not a state function. I have to tell you what's going on at the wall. If I want to know the pressure, I have to know exactly what the shape of the wall is. Okay? So I have 5 minutes. So let me just show a movie, just so when we come back, I'll recap all these things. Uh, okay. Okay. Do you have a pointer? No. Okay, never mind. Okay. Okay, so I'll start with the equilibrium experiment. So the equilibrium experiment is you take a gas, and it's uniformly distributed inside the system. And what I do is I just plug, say, in the middle of the system, I plug a wall. And the wall is such that one side is a gel and the other is, say, a metal. Okay? Now, what I do is I let the wall go. I release it. Okay, now in equilibrium, it's a no-brainer. Pressure is an equation of state, doesn't care about the shape of the potential. And what will happen is that the wall will stay put. Nothing exciting will happen. And what I'm showing you here is numerics of these active Brownian particles. And it's exactly the same experiment. I'll soon let the wall go. And here I have a soft potential, and here I have a hard potential. Okay, and what I'm going to do is I'm going to let this guy go. And what it does, it gets compressed. And it stops at a new equilibrium position, which depends exactly on the potential that's being used to confine the particles. Okay, so that means something pretty dramatic is that I can control forces on objects by changing the chemistry. I don't have to do a big bulk manipulation to change things. I can just change things locally at the wall, just change the chemistry at the wall, and change the forces that this object feels. Okay, it's a pretty dramatic effect. And I want to say that Olivier is hopefully going to talk about it if he proceeds at a pace faster than me. And he's actually measured the lack of equations of state in his experiments. Okay, so so again, just to recap, we have if I have spherical particles and I do this experiment, then again the wall will stay put, because for that specific case when there's no torque on the particles, then this guy doesn't, there's an equation of state. So this guy stays put here. However, once I have a torque, then it stops here. Now this is all ideal gas. So if I plot oh, yeah. Okay. Okay, so if I plot the pressure as a function of the density, then it depends on the shape of the wall. And what I have is, I have two cases. I have, actually it turns out, I'll discuss it in more details later, that a steeper wall, so this is a very steep wall, leads to a smaller pressure for ellipses of the shape that I've shown you before. And a shallow wall leads to a higher pressure. So it's an ideal gas, so it's linear in the density. Okay? But for these guys to be at equilibrium, what they have to have is, of course, they have to have PM equal on both sides. So I have to pick up a line here where the pressures are the same. P1, P is here, so I have a density rho 1 here, a density rho 2 here, and then it's the usual rule that I have the place where it's compressed is such that x times rho 1 plus 1 minus x times rho 2 is equal to the original density of the particles. So that's just the rule for where this guy stops. Okay, so tomorrow what I'm going to do is, first of all, I'll give you some intuition for why all this is happening. And I'll discuss some other examples, and then I'll jump into understanding why in some cases there's no equation of state when there's torque, and in some cases there is an equation of state. And I'll argue at the end of the day, hopefully at the end of tomorrow, that there's a hidden conserved quantity that leads to the existence of an equation of state when there is an equation of state. Okay, so I'll see you tomorrow.